Hey everybody, so this video is going to go over probabilities and counting methods and how we can calculate probability while also incorporating our counting methods ideas that we learned in the last unit. So when we were talking about counting methods, we talked about, I believe, three things. We talked about the fundamental counting principle, we talked about permutations where the order matters, and we talked about combinations where the order does not matter. How does this, how do we involve probability into this? Well, probability, we talked about in the last lesson, is the total number of favorable outcomes over just the total number of outcomes in general. So when we talk about this with just counting methods, we're going to say like the total number of ways with restrictions, so whatever the restriction is in the question. And my total on the bottom is going to be without restrictions. So if we're like not eliminating any possibilities or anything like that, just no restrictions, period. But we're going to take a deeper look at that just through some examples here. So in example number 1, it says Alex, Andrew, and Alberto are competing with 7 other boys to be on their school's cross-country team. All the boys have an equal chance of winning the trial race. Determine the probability that Alex, Andrew, and Alberto will finish first, second, and third in any order. So that is our restriction here, is that they will be first, second, and third, and the order of that does not matter. Now, sorry, I shouldn't say the order doesn't matter. It's just that Alex could be first, second, third. Andrew could be first, second, third. Alberto could be first, second, third. So those are my restrictions. Okay? So if we just consider that, we're going to consider the possibilities that, like how many possibilities where one of them finishes first, the other one finishes second, and then the other one finishes third. So there are 3 ways that one of these 3 boys can finish in first. There are 2 ways, 2 people left over that can finish second, and then 1 that can finish third. So this is just 3 times 2 times 1, which is 6 possible arrangements of how these 3 boys can finish first, second, and third. Now we're going to do the same thing, only now we're going to do it without any restrictions. So any of the boys, not just those 3, can finish first, second, and third. So we have 3 boys here, and there are 7 other boys. So there are 10 total boys. So there are 10 of them that could finish first if they all have an equal chance, 9 that can finish second, 8 that can finish third. When you multiply those out, you get 720. So the probability that these boys will finish first, second, and third is 6 out of 720. Okay? My restrictions here are at the top, and then my non-restrictions are there at the bottom. You can also simplify this fraction to be 1 over 120. Again, I don't know how picky people are with reducing their fractions, so that would be something to ask your teacher, especially going into the final exam. Another way that you can approach this problem is this is 3p3, so that's the number of ways you can arrange the 3 boys in those 3 positions. And then the denominator is 10p3, so you have 10 boys. How many ways can you make those top 3 positions with the 10 boys? And again, if you do those calculations, that's 6 over 720. All right, example number 2 says, Logan spells out the word Saskatchewan with Scrabble tiles. He turns the tiles face down, mixes them up. What is the probability that if he arranges the face down tiles in a line, and then turns them over again, that they're going to spell Saskatchewan? Okay, so Saskatchewan is a word that has multiple repeating letters. So we are going to be looking at permutations with multiple objects or multiple letters. Okay, so this is the second part of the permutation, part of that previous unit. So Saskatchewan has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 letters. And how many of them are repeating? Well, we have 1, 2 S's, and we have 1, 2, 3 A's. And then are there any other repeating letters? Well, there's only one K, there's only one T, C, H, so on. So I believe that these are the only restrictions, but I mean, I was never good at spelling in school, so maybe I'm wrong about that. So the total number of ways, again, just no restrictions, just going back to what we learned in the previous unit, would be 12 factorial divided by 2 factorial, 3 factorial. And again, if you are just using this as a calculator and punching these in, make sure that you put brackets around your denominator so you are getting the correct answer. And some calculators do this, some calculators don't, but you might need to put a time symbol between your factorials in your denominator. So if you do this calculation, and I've done it earlier, it is 39,916,800 possible arrangements of these 12 letters. Okay, so this is my denominator. There's no restrictions on this. My restriction on it is that we want it to spell Saskatchewan. Well, how many ways are there to spell Saskatchewan? There's only one way that we can do it. So the probability is just going to be 1 over 39,916,800. And again, my numerator is only 1 because there is only one way that we can spell Saskatchewan. Okay, so that would be my solution for that. Example number 3, find the probability that a 7-digit number has at least one 8. And there's a hint here underneath that says how many 7-digit numbers have no 8. So what we are going to do is we are going to calculate the number of 7-digit numbers that have no 8. We are going to calculate the total number of ways that we can just make a 7-digit number. And then we're going to do a little bit of subtracting to find how many have at least one 8. All right, so let's run through that. First things first, let's do the total with no restrictions. Restrictions. So I told you, I'm not a good speller. So we have a 7-digit number. So again, I like drawing out the different slots to show the different options, or how many different options are possible for each different digit slot in a 7-digit number. Okay, so if we're just saying there are no restrictions, well, there are 10 total digits. And since there are no restrictions whatsoever, we can have repeating digits. Each of these is just going to be 10. So if you do this calculation, that's 10 to the power of 7, if you want to take a shortcut, which is 10 million possible 7-digit numbers. Now we're going to take into account the hint. So the hint is how many 7-digit numbers have no 8. So if there are no 8s, this is going to be my restriction. So again, I'm going to draw my 7 slots. If I'm saying that there are no 8s, that means that each one of these digits can be anything from 0 to 9 except for the digit 8. So we're taking away one option for each of these digits. So these all have 9 remaining options for the digit. So this is going to be 9 times 9 times 9 times 9, blah, 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 blah. 9 to the power of 7 is 4,782,969. I'm going to assume that's correct. Again, I might have made a mistake on that earlier, but just do 9 to the power of 7, see if you get the same answer. But the question is not asking what is the probability of getting a number that has no 8. We want to calculate the probability that it has at least one 8. Okay, so at least one 8. How we calculate that amount is we're going to take our total without any restrictions, and we're going to subtract from that all of the possibilities that don't have an 8. Because all of my remaining numbers, by just the process of eliminating all the no 8s, all of my remaining numbers would have to have at least one 8 in it. Okay, so we're going to take this 10 million We're going to subtract the 4 million number, and we are left with 5,217,031. So my probability that there is at least one 8 is going to be 5,217,031 over my total with no restrictions is 10 million. And again, we're talking about simplifying fractions. This is a fraction with a numerator and a denominator that are both in the millions. So I don't think the expectation would be for you to simplify this fraction. But if you wanted to, you could change it to a decimal and you could change it to a percent. Just keep in mind on that provincial exam that you have to round your answers to 2 decimal places. So don't round too much. Make sure you at least have 2 numbers after the decimal place. Example 4 has to do with pathways. And now when I was doing this question, I was kind of tripped up on it, I'm not going to lie, because if you look at, so I'll read the question first. It says, what is the probability of going through point C if you're going from A to B? So we have 2 grids here. The grid on the bottom shows you where point C is. The grid on top is going to be our grid where there are no restrictions, where we don't have to pass through that point. And when I looked through this question initially, I was thinking to myself, well, we have 4 moves to the right, and we have 4 moves going down. So in total, I just said, well, it was 8 factorial over 4 factorial, 4 factorial. Again, I'm not going to go into the math behind this. There was a video in the previous unit that talked about examples like this. But the problem with this is that this method is incorrect. And the reason why we can't do this is this method only works with full rectangles. Okay, you don't have to write this down if you are using this to copy your notes, but just kind of keep that in mind. We can only use this method with factorials if our grid was full. So what I mean by that is that this section here and this section here would have to be included to make it a full rectangle. But we don't have that in this case because this chunk here on the bottom left is missing and this chunk on the top right is missing. So the only way to calculate the paths from A to B is by counting the actual paths, which again I went over in that previous lesson, is to count line by line. Okay, so if you didn't watch that, I think we covered it in a previous video, but I'm going to show you here as well. So we're starting at point A. If I'm going from point A just over to the right here, there's only one way that I can do that because I can only travel to the right. Similarly, going down, I can only travel 1 down. And if I keep going to the right, there is still only one way because I can't circle around through the grid to get back to this point. It's just straight to the right. And same with straight going down. And then to figure out the numbers that are in the middle, we add the adjacent numbers together. So to get this point here, I'm going to add 1 and 1, which are my 2 corner points. So there are 2 ways to get to that point. And again, we can just show that visually. We could go right and down, or we could go down and right. Those are the only 2 ways that we can get to that point. So that is why this method works, because our adjacent points, when we add those together, that's going to tell us the number of ways to get to that corner point. So if we keep filling the grid like that, 2 plus 1 is 3, 1 plus 2 is 3, 3 plus 3 is 6. But now that we're at this point 3 here, if we were to keep going to the right, there's nothing to add to keep going that way because, just going to grab another highlighter here. So we've got this point 3 here. So to get to this point, I could go right, right, down. I could go down, right, right, or I could go right, down, right. There's no other way to get to that point. But now that I am here at this point, the only way to get to the point over to the next one to the right, I mean, I'm not adding another path to it. I have to go right to get to that point. And I have to go right again to get to that point at the end. So these two here are also going to be 3. And we can use that same logic going down this way. So I have 3 ways to get to this point right here. So if I keep going down, I still only have 3 ways to get to that point, and I still only have 3 ways to get to that bottom point. And now that we have these 3's here, we can begin adding those adjacent corners again. So I have 6 and 3 is 9, 9 and 3 is 12, 3 and 6 is 9, 9 and 3 is 12, 9 and 9 is 18, 18 and 12 is 30, 12 and 18 is 30, 30 and 30 gives me 60 ways to get from point A to point B. Now again, if we use this method here that I crossed out, so 8 factorial divided by 4 factorial, 4 factorial, would give you actually 70 ways. So by eliminating these boxes, we've eliminated 10 possible paths to get from A to B. So long story short, there are 60 ways to get from A to B. But this isn't our final answer. We want to know what the probability is of going through point C if we're just going from A to B. Okay, so if we look at this one here on the bottom, the good thing about this restriction is that it now creates rectangles. And when we have rectangles or squares, if you want to get more technical, this is a square. Once we have just a box like this, then we can use this method that I crossed out at the beginning. Okay, so I'm going from A to C, and then I'm going from C to B. So basically what we have done, if we are doing this, is we are eliminating these possible roots here, and we are eliminating these possible roots here. So this gives us 2 squares, and when we have a square, like I said, we can now use the factorial method. Okay, so going from A to C, there are 2 moves to the right, and there are 2 moves down. So that's 4 factorial divided by 2 factorial, 2 factorial. So that is 6 possible ways. We can also just see that from our grid up here. Once we got to point C, there were 6 possible ways. And then going from C to B, again, we have a 2 by 2 grid. So that is 4 blocks total divided by 2 factorial, 2 factorial, which is another 6 possible ways. And so when we split it up into 2 separate boxes like this, we multiply our ways together. 6 times 6 gives me 36 possible paths, or 36 ways. Okay, so this is my restriction. My restriction is I have to pass through point B. So the probability, through point C. So the probability of going through point C if we're traveling from A to B is going to be 36 over 60. And again, you can simplify that fraction, you can change it to a decimal, change it to a percentage if you want, but I think that you are safe just keeping it as a fraction. We have one last example here. Thankfully, it is not as involved as any of the previous ones. This one is going to use the fundamental counting principle, which says pizzas can be made with the following options. So there are 3 different kinds of meats, 2 different kinds of sauces, and 3 different kinds of cheese. What is the probability of a pizza being made with these specific ingredients? So again, the fundamental counting principle just says that the total number of ways that we can do something is we just multiply the number of options for each, because we want a meat, and we want a sauce, and we want a cheese. So that word "and" means that we want to multiply. So I have 3 options for meat, 2 options for sauce, 3 options for cheese. When I multiply those together, there are 18 possible pizzas. And if we are using these specific ingredients, well, there is just one option for pepperoni, one option for marinara, one option for mozzarella. So that is just one possible pizza combination. You don't have to show this if you don't want to. I'm just showing you what the restriction is and how we would model it, just like we did with the total without restrictions. So the probability of this is just 1 out of 18. Thankfully, not as involved as any of the other questions. Okay, so there might be a question like this where it's asking you to calculate the number of paths, or we didn't really get into combinations in this lesson, but we could say, what is the probability of making a committee with 4 boys and 5 girls from a total of 10 boys and 18 girls, for example? So that would be an example of where you would use combinations. You would calculate the total with that restriction of boys and girls over just the total without any boy-girl restrictions.